Have you ever swum to the bottom of a swimming pool and felt your ears pop? Or noticed how water pushes harder against your hands the deeper you go? That's liquid pressure at work, and today we are going to explore the laws that govern this fascinating force. Hi everyone! In this session, we'll understand how liquid pressure behaves not just at a single point, but across different depths, directions, and conditions. These laws help engineers build dams, help scientists design submarines, and even help astronauts simulate pressure conditions in training. Before we dive deeper, remember the fundamental formula that governs liquid pressure: P equals H times rho times G, where P is pressure, H is depth, rho is density of the liquid, and G is acceleration due to gravity. Let's now explore these laws one by one. Let's begin with the most intuitive law of liquid pressure. Law 1 says the pressure exerted by a liquid increases with depth. And that makes perfect sense. The deeper you go, the more liquid is stacked above, adding weight and force. This is why dam walls are thicker at the bottom, because the water at the base pushes with greater force. Mathematically, since P equals H times rho times G, pressure is directly proportional to depth H. You can even try this at home. Poke holes at different heights in a plastic bottle, and you'll see that water from the bottom hole jets out the farthest. As you can see in the diagram, the pressure arrows increase in size as we move deeper. Now here's law 2. For the same depth, denser liquids exert more pressure. Let's say you have two containers, one filled with water, the other with mercury. If both are 10 centimeters deep, the mercury will exert much more pressure because it's denser. And again, the formula backs this up: P equals H times rho times G. If rho increases, so does P. That's why instruments that measure pressure, like barometers and manometers, use mercury. Even a small column can exert high pressure. In the visual here, we compare the pressure at the same depth for water, oil, and mercury, with mercury showing the highest force. So next time you hear about heavy liquids, remember, density means pressure. Time for a truly elegant idea. Law 3 says, at any given depth, pressure is the same in all directions. This property is called isotropy, and it explains why submerged objects feel evenly pressed from all sides. No matter which way you turn underwater, the pressure feels the same: left, right, upward, downward. This is the principle behind Pascal's law, which forms the foundation of hydraulic systems. To prove this, take a ball with holes in all directions. When filled with water, the jets will shoot out equally from all sides, showing that pressure acts uniformly. Visual: a water-filled sphere with arrows of equal length coming out radially. This law allows us to build devices that lift cars using just fluid pressure. Now, law 4, the pressure exerted by a liquid always acts perpendicular to the surface it touches. That's why a dam wall curves outward, or why a container feels pressure pushing straight against its sides. This perpendicular force is what we call normal pressure, and it becomes stronger as depth increases. In engineering, this is crucial. Builders design walls and underwater equipment to resist forces coming in at a right angle. In the diagram, you see arrows perpendicular to the surfaces of a dam, growing longer as you move deeper. And yes, divers, deep-sea creatures, and even submarines are designed to withstand this exact kind of force. Let's apply what we've learned. Problem: a tank is filled with a liquid of density 800 kilograms per cubic meter. What is the pressure at a depth of 2.5 meters? Take G as 9.8 meters per second squared. We use P equals H times rho times G. Substitute the values. P equals 2.5 times 800 times 9.8. Now calculate 2.5 into 800 equals to 000 to 000 into 9.8 equals 19,600. So the pressure is 19,600 pascals acting perpendicularly to the container surface. This is how we design storage tanks so they don't burst under pressure at the bottom. Let's quickly revise what we've discovered today about liquid pressure. Pressure increases with depth. The deeper you go, the more weight above. Denser liquids exert more pressure at the same depth. Pressure acts equally in all directions at a particular level. It's isotropic. Pressure always acts perpendicular to the surface it touches. All these are captured by the single equation P equals H times rho times G, and they're not just formulas. They explain how we build dams, how submarines dive, how hydraulic lifts work, and how divers stay safe underwater. I hope this session helped you visualize how pressure behaves inside liquids, not just downward, but all around. See you in the next lesson with more incredible concepts in physics.